Go. All right, we've got homework due tonight. I was just paging through it a little bit, and some of them are tricky. I would love to talk about some of those problems. Let me know. Not extending it, as I mentioned, and you may have just seen me check on everyone's progress, and doesn't, half people have done it, half people haven't. So I'd be happy to talk about some of those. There's a couple I had in mind in particular, but see a couple of questions in the chat. 147, we can take a look at some of those for sure. Does anyone have questions about L'Hopital's rule? These are the ones I pulled out. Let me see which ones I pulled out. Nope, not those. So what did you ask for? 147, this is not the right thing. So 7 was one of the ones I pulled out. Pulled out 9. This is sort of the harder one. Okay, let's start with one of the other ones you said. Yeah, I'm not going to do all these. I'd appreciate some feedback about like what you would like to have what you have questions related to, and I can help clarify those questions. So Rashid, while I'm pulling this up, if you could maybe talk about what it is in particular about these couple problems, or anyone that you'd like to talk about, happy to do that. But I don't think I'm gonna just sort of do all the problems anymore without any feedback, without anyone having their camera on even. This is just not the way class is supposed to run. All right. So let's look at 1 and 4. All right, what do you think about this problem, Rashid?
Yeah, so when I done the problem, it took me a while to get the answer.
So you got the answer.
Yeah, I did get the answer, but so I want to see maybe a way to approach it more easily. Like,
okay,
what
I will do this one, since this is what I would consider a straightforward problem, quote unquote. Yeah. And everyone needs to be able to do this problem. It's a first problem. It's an easy one, quote unquote. Yeah. So the other one's harder than this. So we definitely need to be able to do this, right? So we're being told that X and Y are both functions of time. And so you can see I'm rewriting the equation as just being clear that they're functions of time, so that when we do, and we're given information about dy dt and dx dt, right? That's the kind of things you want to do. So we need to do d over dt to get at those things. And we're going to do it to both sides, of course, right? And this then becomes a product rule, because both x and y's are functions of time, and we're taking the derivative with respect to t. Is that okay?
Yes, yeah.
And so the product rule then would look like this. And I'll just remind you in case people are, when you do like d over dx of x, or sorry, d over dt of x of t, that just becomes dx dt, or you could think about it as x prime. I don't care which notation you use, but sometimes people prefer one of those. I'm going to just do the dx dt notation just to make it a little more clear in my mind. Anyway, so this becomes f prime g plus f g prime, right? That's the product rule on the right hand side. And then 1 is just a constant, and so it just becomes 0.
So what I did was you see where the y and the x are, I switched. That's what was causing the problem.
Okay. I mean, that's the product rule, right? Derivative of the first one, don't do anything to the second, plus don't do anything to the first, derivative of the second. Right? Literally, that's what the product rule says, and so that's what it would look like. And then we're just given a bunch of information, right? Like if you look in the problem, we're being told that dy dt is -1. We're being told x is -3. And then we need to find y, right? And so if x is 3 and x times y equals 1, then you get -3 times y equals -1. This is supposed to be an arrow, sorry. And so then y is 1/3. Right, and so we get 1/3 for this one. And then the last step, the question is, what is dx dt? Right, and so you have something in there for all the values, and then you solve for dx dt. I hate when people write letters like that, sorry. Solve for. Especially confusing in a math class when you write 4 with the number 4. Anyway, does that clarify? This is, again, all the ones
Yes.
further than this are similar-ish, but more complicated in a lot of cases. So it's important we know how to do this one. Like, answer any questions about that one from Rashid or anyone else.
So kind of just like a conceptual question, like,
Yep.
oh, if dy over dt equals -1, how do we like intuitively like try and like what is dx over dt?
Yeah, so in this, in this respect, we're kind of delving into more advanced math. So far, we've only had one variable when we take derivatives, and it's a little more straightforward now. And right now we have 3 variables in this problem. It's x, it's y, and each one of those have this inside t part. And so the way to think about, add a quick page and couple notes. The way to think about dx dt is how x is changing as time changes. Right, that's what the notation means. Dx means how x is changing, dt means as time changes. And so there's no context for this problem, but maybe x is like some variable in one direction and it's changing up and down, and maybe y is changing side to side or something. And so you have both the things changing at the same time. Right, so maybe it's like price of the stock and I don't know, mean value of a stock. I don't know. I'm making things up, but does that answer your question a little bit? That's how we kind of think about these.
Yeah.
And a lot of times early on in math classes, like, and when I mean early on, this is an introduction to calculus, right? No one's had calculus before necessarily when they come to this class. So this is introducing higher level things that eventually, if you really wanted to keep going, you start applying or putting meaning to these things. And some of the later problems kind of illustrate that. Like, I'll pull it up in a second. Number 7, this one puts meaning on it. That's a good one to look at next. Can I answer other questions about this first one though? So like a bunch of the early ones do this kind of thing. All right, so I think 4 is another good one to look at. And so now we have meaning on these things. This is perfect, right? So a price P, so P is price in dollars, and demand X for a product are related by this function, right? So X in there is the demand for the product, P is the price of that product. And then we're being told a couple things down here, right? The price is increasing at some rate. We're being told some value of the price, and we want the rate of change of demand. And so now we have some meaning on these things, right? So the price increasing at $2 means dp dt equals 2. That's what this first part is telling us. Right? The price is changing at a rate of 2. And we know that it's t because it's per month, right? So it's like dollars per month. P is price, right? Yeah. And then the price being $10 is telling us P equals 10, right? So this is similar to the last problem where one is telling us the rate of P, the other one's telling us the value of P, right? And the thing we want to find, it says find the rate of change of demand. So we want to find X is demand, right? dx dt.
And those are all the variables. That's what we're given.
Yep. I mean, that's very similar to this last problem, right? Where it's like you're given, if we kind of look at this example, you're given 2 of the things. We're going to use that information to find the third thing, and then we're going to solve for the 4th thing. So very similar setup. Other questions about that sort of initial setup, right? So we're going to do d over dt of this thing, just like we did on the last one. And it ends up being, if I kind of zoom in a little bit closer, make this a little less thick, right? This is going to be a chain rule because there's a t inside there. We've got a product rule on this one, right? This is a chain rule, and this is just a constant. So that's how we're thinking about approaching this. We're going to plug stuff in. I'll probably just set it up again and then let you sort of think about finishing it, right? But here, when we do d over dt, we're going to get, I'll write out one intermediate step. So it's like 2 times 2x dx dt. The product rule is going to be 10 times f prime g plus f g prime. Right? Very similar to the last product rule we just did a second ago. And I'm just leaving the 10 out front just so we don't have to write 10 a bunch of times. And I should have moved this over to begin with. So I'm going to go ahead and slide it over to start now. And then the next chain rule is 50 times 2 times p times dp dt. And then the constant just goes away, right? So this is, this thing on the left there is very similar. This derivative we just took is like just like the quiz we did last Friday, right? Where x and y were a bunch of functions of time. And then when you did d over dt, you had to think about chain rules and product rules, very similar to this idea. Now we're just sort of using it in a problem, right? So just, it's always a case in math, but especially in this later part of calculus 1, we just kind of put all the things together and we're trying to use it now, right? And I hope I know it's overwhelming, but it's also exciting because we're doing stuff with it. Hopefully that's exciting.
Hey, Professor, I have a quick question for you.
Yeah.
Back towards the start of the problem when you were highlighting with green and figuring out all like the variables, how did you know it was dx over t and not dp over t?
Because early on, right, the first sentence in this problem says that P is the price and X is demand. And so if the rate of change of demand is X, right, and the rate of change of price would be P.
Awesome. Thank you.
Other questions, clarificational things? I don't think I'm going to finish this one. Maybe I'll write the steps down real quick, but this should be the hard part because then the next step is 1. We have all the values except for, oops, I switched accidentally. We don't have, which one? We don't have X, right? Let me highlight this. We're missing this X and this X. We don't have a value for those two things. And so just like in the last problem, right? Like just on the last one, we didn't have this Y and we needed to find the Y. And so we're doing the same thing here. And you just use the equation to find it. So step 1 is to find X using the given equation, right? You just plug things into that long thing. You have a P, you can find the X. Just like the last problem. Step 2, plug in the thing you got and the stuff you were given and solve for the thing you want. Kind of left thinking like, why didn't they use the letter D for demand? But it's probably because then you'd have, when you do D over dt, you'd have like dt, which is a little bit confusing maybe. Anyway, questions? It's the same process as that last one. It's just now has some meaning. I hope this clarifies it a little bit. Is there some algebra involved? Yes. We need to be somewhat confident in our algebra at this stage in math, for sure. Not that I'm expecting everyone is, but those are the kind of things you need to sort of ask questions about, get help with, etc. Feel okay on that one? Did you ask about this one, Rashid? Yes. Feel okay about that
yes.
one? Okay, I did want to also, you asked about 7, which I think was one that I wanted to look at. Do I have that one pulled up still? 4, 1. So I thought maybe people want to talk about 9. I think 7 could be a good one too. And I know this, it's like, oh gosh, this long word problem. It's really not super confusing. The first couple paragraphs are trying to just set the problem up And rather than writing one confusing sentence, it's trying to break it down a lot. So it's just like we have a balloon. You have some balloon that you're blowing up. And so it has a radius, but the radius is changing because you're blowing air into it, right? And so radius is a function of time. Right? When you blow the balloon up, it gets bigger. What did this say in this first paragraph? It's being inflated at a constant rate. How fast is the balloon changing? Blah, 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 blah. Okay, so it's sort of setting up the problem, and then it's sort of breaking it down into pieces. Draw several spheres with different radii. Observe that as the volume changes, the radius and the diameter change. That makes sense. So that means that the volume is also a function of time. Hope that makes sense, right? Because the radius is changing. With me on that? Everything's changing in this. So we have this function for volume, and I would not have been able to pull it off my head. The function, the 4/3 part, would not have gotten that. Anyway, that's the volume of a sphere. And what we're being told is that R and V are both functions of time. So it's really like this. Right? And then it wants us to, let's see the question here, differentiate both sides with respect to t, and then solve for dv dt. Right? So that's what it is. And then the left-hand side is just the answer, right? The left-hand side is just going to be dv dt. And the right-hand side is going to be the answer. And it's a chain rule. Right? This right-hand side, hopefully you can see, becomes 4/3 times 3 times r squared times dr dt. What do you think? So I know that's a little confusing looking, but this would be the answer, right? And you can simplify that. The 3's cancel, for example. What about the second part? Someone answer the second part for me. So the second part's saying, when the balloon is inflated at a constant rate of 20 cubic inches per second, what is that? What derivative does that relate to? How do we answer that? The key is the units that we're given. This part I'm circling right here. That's about that.
Would it be dv over dt?
Yeah, how did you think about that though? Right, so I'm just rewriting it in terms of like a fraction, 20 cubic inches per second. How do we know it's not dr dt or dv dr? I don't know. Thoughts? Sorry, I don't even know who said that before. I wasn't looking.
It was me. I just used the last question and kind of put 2 and 2 together.
Yeah, I mean, that makes sense, right? We're looking at dv dt. It makes sense that would be the case. But the way to think about it is inches cubed, cubic inches, is a volume measurement because it's got 3 dimensions, right? And seconds is a time measurement. And so we're doing volume per time in this, which is how we can think about this as being dv. Oops, I almost circled the wrong one. dv dt, the middle one. And it's how it's changing. So that's why that's where the d comes in. It's how the volume is changing versus time changing. Right? Now the rest of it is just like other problems. And I don't think I want to finish this necessarily, but we're given the same information, right? So how fast is the radius changing? So we want dr dt, right? We're given d is 12. And is there something else we're given here? Diameter is 12. We know the radius is this. Substitute these values. Yeah, I guess that's all we need, those 2 things, right? We'll have to figure out, what are we given? We'll have to figure out r. Just like the last, right? Just like the last 2 problems. You're given almost enough information You just need to use the function to find the last piece. Questions? I mean, does this seem okay? Do people feel a little more comfortable with this after seeing the last couple? It's just asking you to do it twice, right? It says do it when D is 12, do it when D is 16. It'll be the same process. And then it's just saying which one was faster. So your answer is the previous two, get you the last one. Is that okay?
So we have to plug R into the first equation and then compare the two.
You need to
That
find
was the
R, right?
correct. Yeah.
So when you look at this, when you look at the derivative here, when you're plugging things in over on the right, over here, you have dr dt, and you have, you just need to find R, right? So that's where you need to figure out, you plug things into that formula to find it. What is D again? What is it? I forget, what are we doing? D is, oh, it's just the diameter. I'm sorry, I was overthinking that, right? So R is just half the diameter. Don't overthink that one like I just did. Right? You don't need the formula. You're being told the diameter, the radius is half the diameter. Sorry about that. Does that make more sense, Rashid?
Yes, it does.
So R is just 6 here. R is just 8 there. All right, I'd like to move on. Are there other questions about homework problems? I'm slightly concerned no one's asking about 7. We did a little bit of chatting about that in the Slack yesterday, or maybe it was 2 days ago. I don't know, but no thoughts about that? Okay. If you need help later, I'll just remind you that we chat about this stuff in the Slack, and someone was already asking about problem. Well, this is 7, problem 9 I was talking about. So if you have questions about problem 9 later, maybe double check the Slack, or we can chat to clarify it further if it's still not making sense. All right, I'm gonna keep going. Nothing else in the chat here. No other homework question. No one wants to talk about L'Hopital's rule. It's fine. It's no problem at all. I just hope it means it's because it's clear to you and not because you haven't started it. But either way, we can keep going here. All right, so we were talking about these. We did this estimate thing last time. Right, we want to get the area under the curve. This is what we want on the left. We want this green area because if you remember, it adds up total amounts of a function. So it would tell you like the total infections over a time period, or the total births over a time period, or the total amount of money you made over a time period, whatever the function tells you. And last time we talked about how to estimate that kind of with rectangles, right? Now, what I had said, and you can see it says right here, next section, we're going to do the exact value. And so that's what we're moving into. We're like, okay, we know how to do it with rectangles, which is fine. But how do we get the exact value? And so this first page is sort of summarizing where we've been and moving us towards where we're about to be. And the last section might have been a little confusing. And so what I like to try to start with is just a quick summary of that last section. And I'm going to delete this red stuff so I can have a little more room. So what I'm trying to do here is draw the same graph twice, and actually just going to copy this one. And the reason I want to draw the same graph twice is because I want to remind you about the difference between right and left endpoints. Because I tried to explain it last way in a way that derived the idea, but by the end of it, I worry sometimes that it wasn't as clear as I'd like it to be. So I'm going to sort of re-explain both those things and write their formulas down. And I think this is a nice way to sort of refresh ourselves or kind of summarize the things that are on the last couple of pages. Right. And so remember, each one of these times we're trying to estimate the area between 2 points. And so what if A was right here, and let's say B is right where this crosses the x-axis, right? So A and then B. And last time we drew rectangles. And so, but you know, the ones we drew rectangles on were all looked like this. I just kind of did a very simple function that was increasing. And so what happens if you have a function that's increasing and decreasing, right? It's like decreasing on this piece, but then it's increasing during the rest of the piece. How does that look? Well, it ends up being this way if you use left endpoints. So I'm going to try to do the same number of rectangles. Maybe I'll do 1, 2. Remember, the left side of the rectangles are going to be touching here. 3, 4, 5, 6. So I'm trying to, again, the dots are kind of showing the left side of the rectangles are touching. And notice when you do that, it ends up being an overestimate in certain pieces and an underestimate in other locations, right? But if we use right endpoints, the opposite thing happens. So I'm going to do the exact same thing, but if we use right endpoints on that same interval, so let me break up the interval again. 1, 2, 3, 4, 5. We use right endpoints, it all of a sudden ends up being like this. So that one actually doesn't even go anywhere. Right endpoint would be right here. Right endpoint. Right endpoint. Right endpoint. Oops. Right endpoint. It ends up being a completely different picture, a different estimate when we use right endpoints compared to when we use left. And maybe let me try to emphasize the endpoints by making them a slightly different color. So the first one's a little funky because you don't even get anything on the first piece because it's crossing right at that location. Right. So we only end up with these ones. And then same with the last one. And so remember, the formulas for this are as follows. We're summing up function values in both cases. And so this part of it is the same in both cases. What's different are what I ranges between, right? So I've just written the same thing on both cases. The difference is in the first one, I goes from 0 to n minus 1. And in the second case, it goes from 1 to the end, right? But in both cases, you're just doing like base times height. Oops, it's height times base, really. Okay. Again, so this is just showing us when we have a curve that goes up and down, we get vastly different estimates when we do right and left endpoints. Sometimes pieces of it are overestimates, other pieces are underestimates, and it flips when you do the other version of it. Right? And this is perfectly fine. This was a nice sort of starting estimate. But the idea is, and the thing we came up with at the end of last class was, if we want a really good estimate, we would want to just put more rectangles in there, right? And the more rectangles you put in, the less error we end up with. To the point where if we want the exact value, we would want to use infinitely many rectangles. That's what sort of this is saying right here. If we let the n go to infinity, and n is the number of rectangles we have, we end up with the exact value between the 2 points. And so this is the new notation. The integral sign, this which looks like a big S, it means the integral from a to b of the function f of x with respect to x, right? That dx is the same notation we saw before, is thought of as having infinitely many rectangles underneath the curve, is how we're thinking about that. And so that's what we're doing in this section, is we're now, let me just sort of explain this, right? So this right here reads like this, right? The exact area between the function and the x-axis between the points A and B is given by this new expression, right? And this part of it is the integral sign. It means take the integral of this, just like when we do d over dx means take the derivative, right? that now I'm saying when you do the integral with it, which is the big S, it means do the integral. And we'll talk about what that means in a second. But it's just a new notation. Okay. So let me also write this down. I'm just trying to decide if I want to say this. I think I'm just going to write this in another way. So another way to say this notation would be to do the integral from a to b of the function f of x. And it tells us the area between the function and the x-axis, right? So if I put this, see if I can copy this thing again one more time. I've got my curve here one more time. The integral would tell us the exact value that we're looking for. So I'm going from a to b again. And now the integral is going to tell us exactly what we want. It's going to tell us this specific area. No rectangles, tells us the exact value that we want. That tells us that area. Any questions about what I'm trying to say there? No more rectangles, we get that exact value we want. And the key takeaway as you're finished writing this up is the way we do this is we need to know the antiderivative. And so that's where we're getting at the next page. So to evaluate this, we need to know what's known as the antiderivative of the function. And so that's what's leading us to the next page. What is the antiderivative? If we want to get this exact area between the function and the x-axis, how do we do that? And notice how it works, right? It's the area between the function. So if it's above the x-axis, it ends up being like this, right? But if the function's below the x-axis, it ends up being this piece. And so part of what I'm trying to just make clear is the area between the function and the x-axis. Like sometimes people think we're finding this area, for example, right? If you're not clear about what's going on, that's the area above the function, really, right? We want the area bounded between the function and the x-axis, which is this and this. It's another thing I want to make sure is clear. Okay, thoughts about that? Any questions so far? I'm going to talk about what the antiderivative is here. I'd be happy to clarify anything. Anything at all? Okay, so the question is, what is an antiderivative, right? If we want to do this, we need to know the antiderivative. Let me just page ahead. Okay, good. So here's a whole list of antiderivative rules that we'll talk about in a minute. Just like we had derivative rules, we've got antiderivative rules. But before we look at that, let's explore the idea, right? And the word antiderivative should have a specific meaning to you. And it doesn't mean that you hate derivatives, right? Sometimes people, I feel like, think, oh, antiderivatives mean I'm antiderivative. This is great. Hate derivatives, so I'm antiderivative. No, it doesn't mean we hate derivatives. It means the opposite of derivatives is the way you want to think about that. It means, let's read what it says right here, right? The antiderivative of a little function, and I'll refer to this as, I know it sounds weird, but I'll refer to it as little f, is a function capital F, which I'll often call big F, such that when you take the derivative of the big F, you get the little f. In other words, right, when you do d over dx of capital F, you get the little one. And so I'll try to differentiate big F and little f with capital, and then I try to do a little tail on the little one. right? So you see how the word antiderivative makes sense? We're doing the opposite of derivative. We're trying to like think about, what did I take the derivative of that got me this, right? That's sort of the thought process. And so if we're looking at this first problem, it'd be really great if everyone just focused in and thought about this idea. If our little f is 3x squared, right? What is big F? In other words, we want to think about, I take the derivative of what to get 3x squared, right? That's what we're trying to think about. That's the notation I'm trying to sort of get across here, right? What do I need to take the derivative of to give me 3x squared?
X cubed.
Yeah, x cubed, right? So I'm actually going to erase the what part and put x cubed, right? Because it's like, oh yeah, you bring down the 3, subtract 1 off the power, and we would get 3x squared. And so this is sort of telling us that big F equals x cubed is an antiderivative of 3x squared. Because when we take the derivative, we get 3x squared. Okay, that's sort of the goal I'm trying to get across. But I'm also highlighting this word "and," right? It's not the only one. It's just one of the options. What are there other? What am I trying to say here? Like, what is another thing we could take the derivative of? Maybe that would also work. All right, what goes away when we take derivatives and just kind of gets lost?
Constants.
Yeah, constants just go away when we take the derivative, right? So if we had x cubed plus any constant, it would also, and we took the derivative, it would also be 3x squared. So let's write that down, and then we'll kind of build on this. So x cubed is not a unique antiderivative of 3x squared, because x cubed plus any constant also works. And if that's still not clear, I'm just going to write down a couple examples and show you what I mean. So for example, capital F of x could be x cubed plus 2. Right? Capital F could be x cubed plus 100. Could be x cubed plus any constant, like, I don't know, pi, whatever. Right? If you take the derivative of any one of those three things, the constant just goes away and you get 3x squared, but each one's a different function. And so what we're trying to say here is these antiderivatives are not unique, right? So if I took the derivative of any of those three things on the left, you get 3x squared because the constant just goes away. And so if we're trying to recover the constant, we don't know what it used to be, right? And so that equals 3x squared for all examples on the left. And infinitely many more, right? You could add any constant on there. And so that sort of gives us the idea of, okay, antiderivatives are not unique. And so there's the idea of the sort of the antiderivative of the variable part, but then there's the family, which is now at the bottom of the page. The family of antiderivatives thinks about, okay, well, we need to put a plus c on the end of there because there might have been a constant there that we lost along the way. And so that's what this part says. This is the family of antiderivatives now, right? So when we take the integral of a little function, we do the antiderivative, then we also throw on a plus c is what this is saying. All right, so I'm going to write that down in words a little bit here. Excuse me. And also this is a good place to clarify this dx part. Don't get too overwhelmed by that or confused. It's just like when we do d over dx, for example, right? It just tells us the variable that's in there. This just means with respect to x. Just want to throw that on there. And so what this is saying, this notation, we want to be able to read this stuff, right? This is saying when we do the integral of little function f, we get the antiderivative, which is capital F. But then we also do plus c for any constant that we lost along the way. So that's the way I think about a list. For any, we gotta think about it for any constant that existed before the derivative. Right, we're trying to undo the derivative, antiderivative. So what, this whole page is trying to say, well, if we had a constant there, it's just lost. We can't figure out what it is. I mean, there's ways to figure it out, which we'll talk about a little later, but for now, we just put a plus c to represent that. Okay. Thoughts about what I'm trying to say about difference between an antiderivative and the family? Okay, so what is the antiderivative then? How do we figure out what that is? Let's keep moving forward with this. So what I'm going to make the note here is see the next 2 pages for common antiderivatives. And I'm going to go flip into that. The antiderivative of this function. And so let's look at the rules that apply before we do that, okay? So I'm going to go to the next page here, and here are all the rules for antiderivatives. And you can see, if we kind of figure out, look at this page and think about how it works, A and C are all going to be constants. So like here's a constant. These are all constants. All right, is there another A in here somewhere? No. So that's the only A, right? So the things I'm highlighting, or I'm close to highlighting, are just constants. And the way this is working, it's telling us when you have this kind of functional form, the antiderivative is this, right? And then we think about this part as being the family of antiderivatives. And so the difference between this and this is just a plus c. Right, you see that? It's literally the same thing, and all this is just you have a plus c over on the right to represent the family. Right? And then I would also point this out. In all the cases here, we have little f being the function and big F is the antiderivative, right? So this is a thing you're given usually, and this part is the antiderivative. Okay. And so the way, the nice thing about this is it's like, oh, a bunch of things we need to memorize. How are we going to do this again? I already memorized all these other things. All these rules are just the opposite of the derivative rules. So we already know them, right? Like look at the first one. Look at this first one. I'm just going to circle in green. I like to call this one the anti-power rule, right? When you do the power rule, you bring down the power and multiply it and subtract 1 off the power, right? This is the opposite. You add 1 to the power instead of subtracting. And then instead of multiplying by that, you divide by it, right? Literally just doing the opposite, right? Look at the constant rule, right? Usually when you do d over dx of ax, you get a, right? The x goes away. And so here we're doing the opposite. We're starting with the a, and we're going back to ax. And that's what this says. When you start out with a constant and you do the integral, you just throw an x on top of it, right? So we're undoing the derivative rules. E to the x is the same, right? When you take the derivative of e to the x, it stays the same. That means when you integrate it, it also stays the same. right? So we already know these rules. This is the thing I would really just emphasize is we're doing the opposite of the derivative rules. Now, some of them are a little funky, like ln, because we didn't really have, when you think about the derivative of ln, it becomes 1 over x. And so we have that rule right here, right? Because we know when we differentiate ln, we get 1 over x. And so we're doing the opposite here. When you integrate 1 over x, you get ln. So that's different than the ln rule. This ln rule, and I would say this rule doesn't come up a ton. Notice the sine and cosine rule, right? The derivative of sine is cosine. That's from the derivative section. That means when we integrate cosine, we get sine, right? And that's what this one says right here. So yeah, I don't want to spend a ton of time on these rules because we already know them. I'm just trying to point out how we're thinking about it. We're doing the opposite of derivatives. Can I clarify something about that? And then to see how we have the regular one in the middle and then the family on the right. And literally it's just throwing the plus c on here. That's the only difference. So let's look at that first example. The first example is this one, right? We've got a bunch of anti-power rules, quote unquote. And so we're going to add one to the exponent. I can't really put both those. I guess I could do this, right? This one right here is just an application of this. Add one to the powers, put on the power. Oh, and then the one on the end is a constant, right? This one is going to be the constant rule. With me on that, I'm going to erase those colors in a second there, but just kind of identifying what rules we're going to use in a second. Okay, so let's do that. And I'll write out the details on this first one, of course. So let's integrate g of y dy and start using that notation. Squiggly s thing means integrate. Dy means y is the variable we're going to use, right? And so this becomes this. Okay. And we're going to use those three things I just talked about. Oh, I guess I should mention this too, right? Let me go down to the rules again. We also have, I forgot the rules at the bottom, what to do when we have constants and what to do when we have sums. And it's the same thing with derivatives. Remember, with derivatives, you just kind of do them separately. And that's what this is saying. It's like, hey, when you integrate h plus g, you just get big H plus big G. So you just do them separately, right? When you have a constant, you just ignore the constant and you just integrate the function. Same kind of idea as derivatives, right? So on this one, even though we're integrating three separate things, you just do them one at a time. And really the 2 kind of just comes right out in front. We actually ignore the 2. So let me do that too. Right, just being kind of real careful. When you have three separate things, just do them separately. And then we do the quote unquote anti-power rule. And so here's what that looks like. Add 1 to the power, divide by the power. Right. And I'm going to do this one time. And then we put a plus c. And I'm only going to do it this way once, and I'll explain what I mean in a second. And then we add 1 to the power, divide by the power. And then we have a second constant. And then the 1 becomes a y, that's the constant rule, plus C3. And so here is our simplified derivative. And instead of writing three separate c's, we just kind of think about them collapsing into a fourth c. And so I don't need people to do this, in practice. But what I'm trying to say is when you think about them individually, they each get a plus c, but then those collapse into this fourth c. And so really you only need to add on 1 plus c, right? So I don't need to necessarily see that. What I'm trying to say is each one gets 1, they collapse into 1. And so really the way you would want to write this is y cubed over 3 plus y squared plus y plus some generic c that accounts for all of them. All right, and that's our first antiderivative. That's great. Let's pause there and see how that looks. Clarify anything there? Okay. So we're really, we've only looked at the first couple rules, and the third one's pretty straightforward too, right? We haven't looked at it, but that's pretty easy. We'll get into some of these more complicated ones as we move on, and then you can see down at the bottom here. Where am I looking? Later on, I'm just going to kind of flash ahead just for one quick second. We'll talk about doing more complicated ones. So eventually we want to think about undoing the chain rule, right? This is the chain rule being shown right now. And to undo the chain rule requires some more advanced methods. So we're eventually going to get to that. But let's do some more sort of more basic ones first, quote unquote. So no questions about this one? Is everyone all set with that? Can I keep going? I don't want to move it too quick. Okay, so let's do another quote unquote simple one, right? So we have these couple integral properties. The first one says, and I just used it a second ago, right? If you have something like 2x dx, you just ignore the 2 and you just focus on the x, right? I just did that one in a second ago. And we just did this one too, right? If you have like x plus 1 and you want to integrate that, that's not any more complicated than just doing them separately. Right, and so let's do that on this first problem. Right, so when we do this one, we just we just think about them separately, add 1 to the power, divide by the power. Right? The 2 is a constant, the 2 just gets the x, right? This is the constant rule. And then we throw the plus c on it. Now, the cool thing that, I don't know, maybe cool isn't a stretch, but the nice thing about these, and I guess maybe we should simplify it, 2 is divisible by, or 4 is divisible by 2. The nice thing about these antiderivatives is we can always check our work, right? Because we know how to take derivatives. And so we can always just check to see if we got the right answer by just differentiating this thing. And I would never sort of ask you to do that in a test or anything, but it's a good mental check, right? And this is an easy one to do, especially if it's a power rule. You can just look at it and say, if I take the derivative, do I get back to the original? Let's see, right? Bring down the power, subtract off the power. Sorry, that should be an x. Okay, yes, we got back to the original. So that makes me feel good. So that is the answer. All right, what do you think? Is this okay? You guys kind of understand the idea here a little bit?
So in 2dx, instead of just, because like since there's a constant rule in it, in the derivative it would be 0. So instead of being 0, we just add an x.
I'm sorry, can you say that one more time?
Like you have the constant rule for 2, but if you were taking the derivative of it, it would be 0. Since it's the opposite, you just add an x instead of converting it to 0.
Yeah, so what you're saying is when you take the derivative of 2, you get 0.
Yeah.
That's why when we integrate nothing, we do a plus c, because we don't, the 2 just goes away. And so when we integrate nothing, we don't know that it used to be a 2. So we just do a plus c, where c is any constant.
Mhm.
Now, if we differentiated 2x, the x goes away and we just get 2, right? Is that okay?
Yeah.
And so that's why if we integrate just 2, we get 2x. Now we put the plus c on there because there could have been a constant, but we're thinking about going backwards from the derivative. Like, what did we take the derivative of to get to, is the way we think about that. And we think, oh yeah, there used to be an x to the 1.
Okay. Thank you.
Yeah, other clarificational thoughts? Thank you for that thing. So, my goal here is actually just to let you think about the rest of the ones on this page. And I didn't specifically talk about the rules, but you can look at the rules, right? We know the rule for the sine functions right at the top there. The rule for e and tangent are right at the top there. And so I would ask you to think about those. Let me set this one up, though. Remember, how do we do ones like this with derivatives? What was the sort of the approach? Remember? If we differentiate radicals or 1 over x squareds, how did we do that in derivatives? Anyone? Right, like if this didn't say integral, this said d over dx, what did we do? Did it a whole bunch of times. It was on the test. Pretty sure people know how to do that, I think.
Set it as x to the 1/2.
Yeah, we make them exponents, right? We make, so x cubed is an exponent, but the square root becomes 1/2, right? The x to the -2, or x squared, excuse me, becomes x to the -2. And so we would do the same thing here. We think about this as x to the 1/2, x to the -2, and then use the anti-power rule, quote unquote. Right now, each one of these things looks like this, right? So add 1 to the power, divide by the new power. All right, take a second and explore this a little bit. So try this one, 1, 2, 3. Take a look at the rules. Don't forget to add a constant, right? So you're going to throw a plus c on there. Now is a good chance to just sort of get your hands dirty right away with some of this. It's new stuff, but it's stuff that you should be familiar with because we know the derivative rules, right? So just do the opposite of those rules. And if that doesn't make sense quite yet, just use the references up here. Right, so here's how you do tangent, for example. E to the x stays the same, etc. Just give you a minute to do that. I've also realized too that these are an opportunity if people have a question and they want to just, like, if we were in person right now, I'd be walking around the classroom sort of giving people one-on-one help. But people would like that one-on-one help. We can do a quick breakout room. I've sort of really recently realized. So anyway, I could do something like this. I could like open up a room, and then if anyone wanted to talk to me, they could like pop into the breakout room. Anyway, just an idea there if you wanted some sort of one-on-one help in these strange times. Maybe I'll start writing down a few details here. So on this first one, we just add 1 to the power. Oops. Divide by the power. Add 1 to the power. Divide by the power. Add 1 to the power. Divide by the power. Throw on that plus C. And then when we divide by that fraction, man, that's horrible. And then we've got the -1 in the bottom, so this can be simplified a little bit more. Could be x to the 4th over 4. Remember, the 3/2 becomes 2/3 and multiplies. Then when you divide by -1, just makes that thing negative. So here's a nice simplified version of that. What do you think? Is that okay? You know, the sine and cosine ones are ones that trip me up pretty regularly. The only thing I ever remember is that the derivative of sine is cosine, and using that, you can kind of reason through the other ones, but it still doesn't stop me from messing things up. So anyway, just using those rules, right? Sine becomes minus cosine. And we do the plus C. And again, you can always just like double check that, right? Like, does that make sense? If you've got the derivative rules in your mind pretty good, if you differentiate minus cosine, cosine becomes minus sine, right? So we have like minus sine. Yes, the minuses cancel and we get back to the original. Okay, good. Right, just a quick mental check is helpful. Tangent's a weird one, right? That's definitely not one that I have committed to memory. It becomes this, right? It's a little bit strange. But we just apply that. And e to the x is one of those nice ones, right? It just stays the same. E to the x doesn't change, or e to the t in this case. And then we end up with a double negative. We have like minus, and then tangent becomes minus ln, absolute value of cosine. And so the double negatives become a plus. All right, what do you think? All right, I'm going to write one more down here just so I'm just kind of looking at the list and seeing that we don't have one for ln. So what if we integrated, let's do another root one. How are we doing on time? We're doing great. All right, so we have that root, right? Cube root of t squared becomes t to the 2/3, right? And notice how 1 over t, if you tried to think about the integral of 1 over t and you were thinking about that as t to the -1, right? Then adding 1 to the power would be 0. And then dividing by that, oops, that's no good, right? So that's why the integral of 1 over t is the one case where you don't think about it as a power. Instead, we think about it as being ln. Right? And we know that when we take the derivative of ln, it becomes 1 over x. And so that makes sense. We're undoing that. Right? And so 2/3, add 1 to that. 1 plus 2/3 is 5/3. And 1 over t becomes ln. And of course, we shouldn't leave it like that. So this becomes 3/5. Okay. Hopefully we feel good about these kind of basic ones. Just pause there. Thoughts? Seems okay. Questions? doing here? I think, let me look at the schedule real quick and I'll answer some questions if you got them. Yeah, I think I'm going to stop here before going too much further. Maybe I'll set up the next thing, but I'm not going to go too deep into it. I'm just going to stop here, actually. There's no point in doing that. Questions? Can I clarify something? And we got some more time if people want to look at homework or anything. Happy to do that. Otherwise, that's all I've got. Thanks, everyone. Didn't want to talk about any homework or anything?
Is there any chance we can look over related rates problem 9?
Yeah, let's look at that one. Actually, I think I already copied that one over. Oh, not this again. One second here. Let me actually just save these into the homework file before I forget. Okay. So did you set this one up at all? that?
Yeah, I think so.
Is that Amon asking?
Amon, yep.
Great. So the triangle looks like this. And what were you thinking were sides that are moving?
Well, I had C and well, aren't all three of the sides moving? Because the rope on the vertical side is getting shorter as the rope on the hypotenuse is getting longer, and then he's getting further away.
This is the confusing part of this problem, I think. And I remember the first time I looked at this, it was definitely confusing to me. Let me just remind myself, I wrote the solution down. I did this one previously. So the question is, so did you label it like this, A, B, C? C is usually that side, but A and B, is that all right?
Yep.
So I agree that, this side is definitely changing. And this side is also changing. But the idea is, even though, is it a weight or something that's being pulled? Yeah, so there's like a weight right here that is going up, but that side length doesn't change. Like if we drew this triangle later, the person's moving further away, and so it might look like this or something. This is like a later version of the triangle. And maybe the weight is higher up, but this side length is the same length. You see what I'm saying there? Like the weight is moving, but that distance from like the pivot point to where the ground, for example, is not changing. And so that is the tricky part of this is, yes, the weight is moving, but that one side is not changing. And so C prime, so I would say C is a function of time. Oops, B is a function of time, but A is fixed. But A prime is 0 is the way we would think about that. So that's the thing that oftentimes people miss, that I missed myself when I first started working on this. I don't know, last time I taught this class. Yeah. And so if we have a squared plus b squared equals c squared, which is the relationship you want to use here, these two things are functions of time, but the other one's not. And so when we differentiate, this one becomes 0. We just get 0 plus 2b prime. That makes sense. Does that clarify it for you? And then you're given things about C prime and stuff like that, right? We're being told. So we want C prime actually. How fast is the weight rising? That's another confusing part is, right, it seems like we want A prime, but the weight moving is C prime. So in other words, this is asking for C prime because it's one continuous row. Yeah, that makes it particularly tricky. And that's why I was kind of hoping someone was going to ask about this. I appreciate that folks are still sticking around to think about this. Who knows? Maybe people will watch this video later. I don't know. Does that clarify it for you? Do you think you can finish it?
Thank you.
Or anyone else? That seem all right? You're probably going to have to do the same thing where we're being told, I guess, let me just sort of set it up a little bit more. We want C prime, right? And we're given the person walks away at B prime equals 2. Total rope length of 50. So we know A plus C equals 50. That's another tricky thing. And there's some other piece I'm missing. Oh, and we know A is 25. So that means, and this, your numbers might be different. Sorry, this is getting a bit small, but that means C is 25. And then we're being told B is either 10 or 30. Anyway, I don't know if people are looking for me to do that more. Other questions? Should I go in more? I help with other things. People just working on this. I've got another meeting in a minute here.
All right. I'm gonna head out. Thank you.
Sure thing.
Thank you very much.
See ya.
Thank you.
Thank you.
Bye, guys. I'm gonna get going too.